Hello everyone, I'm Stefan. Today I will talk about the paper towards facilities for modeling and synthesis of architectures for resource allocation problem in systems engineering. Well, first I will go through the context and motivation as the topic is slightly different from classical SPLC1, highlighting the needs towards facilities for modeling and synthesis of architectures and towards benefits of variability and more precisely the Clapper approach to address an allocation problem. Then I'll make a focus on the heterogeneous hardware resource allocation problem in the industrial case study. A brief word about the Clapper approach, provide insights on the experiments and observations made, and I'll conclude. Systems architecture exploration is about characterizing the problem space and determining by synthesis suitable solutions in the solution space that address stakeholder concerns. The state of the practice in model-based system engineering reveals that efforts generally favor solutions, solution analysis over exploring a set of candidate architectures. Dealing with complex systems, exploring architectural design spaces has often become beyond human capacity. Indeed, model-based system engineering must include assistance to the system designers in identifying candidate architectures to subsequently analyze trade-offs. It highlights the needs for efficient architecture synthesis. Well, resolution solution exists, but the need goes further and goes towards high-level declarative language for architects or system engineers in order to characterize the architectural design space and with viable resolution performances indeed. Well, traditional systems engineering design problems are the following: system sizings, where some design parameters are not fixed, configuration setting, where some components are not selected, resource allocation, the one which is today's concerns, where some resources are not allocated, architectural synthesis, which is a mix of everything. At this step, the model of the system to be defined must include degree of freedom, unfixed parameters, variant descriptions, which is a concern traditionally addressed by the SPL community. So the objective of this study is to explore the advantages of designing and configuring variability problems to solve the resource allocation, and more precisely to report on the use of the Clapper modeling language and its gateway to the Shocker solver, which is a constraint solver programming paradigm. This on an implemented industrial case study. Well, in many domains of embedded systems, task allocation is typically addressed as a subproblem of scheduling and real-time multiple systems. In our case, the allocation problem consists in a dedicated task deployment onto heterogeneous hardware resources like general purpose GPP, dedicated GPU, and FPGA, which communicate through PCI buses or Ethernet. The modeling consists of first a data processing application, the set of necessary functions represented as data flow oriented graph. Here, execution times are pre-calculated. In fact, we use models of the systems under development to obtain performance predictions with sufficient accuracy already prior to the implementation. The scheduling of actors in the application graph follows a data flow token-based policy and can process. And a given actor produces, after each firing, a fixed size token to its single actor. The resource constraint hardware platform consists in 4 boards, 2 boards with GPP, GPU, FPGA, and 2 boards without FPGA. Has processor memories, PCI buses, Ethernet between. The open mapping deployment allocation between data flow nodes and hardware nodes is subject to constraints like residence, unique deployment, compatible connection, so on and so forth. Respecting capacity is key, processor and communication connection boundaries, for example. Well, an allocation problem represents here a permutation with repetition, which assigns one computational unit to each function or data flow communication. It implies that the search space increases exponentially with the number of data flow hardware elements. The application in itself, taken as an example, is representative of a class of data flow signal or image processing application hosted in a real-time sensor system. Generally subject to strong constraints on size, weight, and power, and process latency. It implements an image processing chain that take periodic 2D frames as input and performs a sequence of transformation to detect and process objects of interest. Well, briefly, let's give a word about Clapher and its toolchain. On the one side, the Clapher constructs are Clapher, which unify the concept of classes, association, and properties. We have single inheritance, Clapher nesting, Clapher reference, bag, set, multiplicity. Clapher supports constraints written in first-order predicate logic. It has both existential and universal quantifiers, sets, and relations. On the other side, the Shocker domain is a typical CSP, which means variables with domains and constraints. The Clapher toolchains include the Clapher compiler, which translates models in Clapher into an intermediate format for reasoning and processing with backend tools. In our case, the Shocker server compiles the intermediate model down to a set of variables and constraints in the Shocker constraint in CSP program. Note that the Shocker server module defines specific propagators for Clapher constraints. Well, the Clapher language offers many constraints and therefore many ways to encode the problem. Different Clapher models were encoded, defining benchmarks to construct the experiments. We provide the full detail of the modeling in a GitHub reference. The experiment performed on the modeling includes modeling properties and variability ranges, as we had to scale down and round all values to the nearest integer. And also, and mainly, selecting the deploy to allocate to a modeling scheme as illustrated by the code on the right. And finally, the hardware platform allocation constraints, which has to be defined communication for communication and treatment penalties. It implies introducing intermediate resolution variables and queries definition. One point, the resolution phase is crucial. In Choco, the topology of the search tree depends entirely on the order in which the resolution variables are instated, as well as the order in which the values are evaluated. One of the parameters available in Clapher is the branching priority, which is parameter from the Shocker server library. Branching priority affects the resolution variable order list as well as the solver resolution policy. Well, we perform experiments, and here the table shows the effects of the branching, which reduces drastically the resolution time. More details are provided in the paper. Well, 12 observations are pointed out. First, to highlight the limits of the integers to deal with properties from different dimensions and scales. Then that with the experimented version of the tool, the classical feature modeling approach is not, whereas it could intuitively be, it was not the best option to use when modeling an allocation problem. Ops 4 and 5 well shows that the limits of the current Shocker server implementation, and it highlights areas for improvement regarding translation in the resolution space. The following goes towards the benefits of having to deal with high-level architectural concepts to express them. And finally, the essential element of the study summed by the last 4 observations, which is the importance of the resolution to solve the problem. Moreover, the result on the experiment shows that the applied strategy may need to evolve when developing the model, which is interesting. Well, in conclusion, we have successfully encoded the industrial application in Cloudflare without the expert of the approach, which can be an improvement in the future. And as said, 12 observations were carried out on the use of the language, the importance of the resolution strategy. The experiments show that the approach of the variability design problems, and more particularly Cloudflare, offers interesting features to address systems engineering problem resolution. However, work still has to be done towards filling the gap between architectural formalisms and constraint programming in order to obtain a gain in the resolution efficiency and have maybe generic and viable approach. Well, one difficulty is to maintain generosity and moderation in the modeling, which can be done at the expense of the efficiency of the resolution. Well, a compromise must be found between modeling at the architectural level, which is and must be generic in nature for the architect, and modeling for resolution, which to be most effective must be specific depending on the type of problem to be solved. Well, several approaches are possible to help the efficiency of the resolution. Implementation of specific declarative resolution strategy, which would imply adapted means of expression of these strategies, or an analysis of the model to suggest and apply adapted strategies or guidelines to assist in the modeling and resolution. Well, that's all for today. Thank you.